Hi guys, so my name is Rebecca Melkerson. In the summer I was studying computational studies of particle dynamics during magnetic reconnection. So magnetic reconnection is a plasma event during which magnetic field lines change topology and convert magnetic energy to thermal and kinetic particle energies. And this occurs when magnetic field lines meet pointing in opposite directions, as they do in A. And then in B, we see that they have started to change topology and reconnect. And in C, we have reconnection has occurred and the topology has changed. This light-colored oval is what we call the reconnected region, and we have these dotted lines to show you the X line. So reconnection occurs in many space and astrophysical plasmas, and the resultant charged particles have potentially hazardous consequences upon reaching Earth, for example, interfering with telecommunications, navigation, power grids, etc. So scientists are really interested in studying reconnection to hopefully mitigate those issues. On the right, I have a figure of space where reconnection occurs and some contributing phenomena. So A is the solar wind, which is this outflow of charged particles from the sun, and it pulls the coronal magnetic field along the way, creating the heliospheric magnetic field here, which is B. The solar wind flows past Earth and pulls out Earth's magnetic field, creating the magnetotail, which we see as C. And reconnection does occur here when the Earth's magnetic field lines meet pointing opposite directions. And then D, we have the magnetopods, which is another location for reconnection, where the heliospheric magnetic field reconnects with Earth's magnetic field. E is to represent reconnection at the sun, which contributes to solar flares and coronal mass ejections, and that's where some hazardous charged particles come from that float towards Earth. F is to represent reconnection on Earth because although plasmas are not as frequent or prevalent on Earth, reconnection can occur in fusion devices such as tokamaks and accelerators. And finally, G is to represent the magnetospheric multi-scale mission, which is these 4 satellites that fly in a tetrahedron to collect 3D data on reconnection. And on the left, I have an image of some auroras just to show you that there are some not so hazardous effects of reconnection, some that are kind of beautiful. So I just included that for you guys. So I said computational studies. That means we're doing simulations. Our simulations, we use particle and cell simulations on massively parallel code. And we can do 2D or 3D reconnection simulations. And this reconnection occurs in the XY plane. And our code tracks the electric field, the magnetic field, electron and ion currents, electron and ion pressure tensors, and electron and ion particle densities. And from that, we can calculate lots of other things. I've included an example image of the out-of-plane electron current, JEZ, just so you can see what we see when we do these simulations, and overplotted the magnetic field. And you can see that we actually have an X line here, and so this would be where reconnection is happening. So my project was kind of divided into 2 parts. The first part was looking at power laws and electron energy distributions. Power laws arise when the governing physical phenomena or processes are nominally scale invariant, and these happen all over nature, and scientists get really excited about them. So, and they actually are shown in this 3D data of reconnection, but the simulations have had difficulty showing them, and this on the right, we have an example from some of the 3D data, and we see this power law here that spans about 2 orders of magnitude. And power laws are non-thermal electron energy distribution functions, and like I said, simulations have had difficulty showing them, which is why when we heard of an example or a recent claim of power law production in simulations, we were interested, and because up until then, nobody's really seen them. So we decided to look at a 3D simulation of our own with similar parameters. It was only different in our guide field, which is 2 versus 1, but our experience with simulations have shown that that really shouldn't matter. So we compared the figures just to show that our simulations were pretty similar. So on the left, we have E parallel averaged over the Z direction. E parallel would be E dotted with the magnetic field. And then on the right, we have the spatial distribution of E parallel through the central plane, which would be X equals 0 for our simulations. And we see that our figures are pretty similar to the other simulation. But we're not convinced that these simulations are actually showing power laws, and we think that for 2 reasons. First off, the linear span that they're showing is only about 1 order of magnitude from here to here, but as we saw from the example 3D data, that the span is actually more like 2 or more orders of magnitude. And we also argue that you can have 2 Gaussians that are added together and give the appearance of a linear region, and a Gaussian would be about this from the initial system, and you can see that this kind of looks like there are two added that give a linear region. So the second part of my project was on looking at the effect of beta on electron energization. Beta is the ratio of thermal to magnetic pressure. We are doing 2D simulations with 5 different values of beta. And we utilized a guiding center model to evaluate this electron energization, and which just means that it omits the small scale movement of the electrons in favor of the overall particle movement. And these terms represent direct electric field acceleration, Fermi acceleration, and acceleration by magnetic moment conservation. So here's a plot of the data that we got from the looking at beta, and we find that the magnetic moment and magnetic moment and directed field acceleration are definitely smaller than the Fermi accelerations, Fermi being the most important factor. And we see that Fermi actually has an uptick for low beta right here that we weren't expecting, and we don't understand why, so that's something that we need to study further. And I said we did 5 simulations, so you see a lot of plots here. We actually did 4 more with a higher number of particles per grid, because our starting number was fairly low, and we just wanted to confirm that that shouldn't affect our simulations, so we could justify doing faster simulations. On the right, I've included some example figures of these different types of acceleration, just to give you an example. And you can see this would be where reconnection is occurring, and we would get these values by averaging over these boxes as shown. So just to summarize, we analyzed a 3D simulation with similar parameters to the one planned to show power loss, but we still do not believe that our simulations or their simulations are really showing power loss. And we also find that Fermi acceleration is generally the most significant contributor to electron energization, with an uptick for low beta, but we do not yet understand why. And thank you to Trend and the National Science Foundation for funding.